So first of all, thank you everybody for taking part, especially our two esteemed speakers, but also all the students across all of Europe. It's very nice to see such keen interest everywhere, basically. And thank you for chiming in, on the Space Week, but also, as you've seen, this is part of the CosmoVerse Cost Action, which is basically a network across all of Europe, but even more than that, a global network, where we're trying to coordinate efforts across different research groups, different countries, to really tackle some of the most pressing problems in cosmology today, as you will understand from the nice presentations that we have coming up. So also to say, it would be great also if you can follow us on Facebook or Twitter, now X, to go on to our first speaker, Dr. Elsa Teixeira.
To introduce her a little bit, she is finishing her Ph.D. this year at the School of Mathematics and Statistics at Sheffield University under the supervision of Professor Carsten van der Bruck. She is also a postdoctoral researcher at CNRS, based at the Laboratoire Univers et Particules de Montpellier. Her research revolves mainly about understanding the nature of the dark sector of the universe.
So, Elsa, would you like to unmute and share your presentation?
Hi, thank you. So hello everyone, thank you for joining. My name is Elsa. So I'll just be giving a brief introduction to the what I call the cosmic recipe, but this is basically just discussing what are the main components of the present universe and how it has been evolving with time. And then Professor Benjamin will give you a more thorough explanation throughout all of these topics, especially this late time cosmology that we are going to see here. So basically, I think the first question we can ask is what is cosmology? Because it is not something we hear that often, right? So usually we hear about astronomy or we hear about astrophysics, and that is a bit more intuitive for us than cosmology. So basically, we can start with the idea of what is astronomy. So we can think in the past. So when we think, for instance, about the Greek philosophers, we would think that astronomy was basically, we had no observational tools. So we still didn't have a very, let's say, refined mathematical formulation for what was happening physically in the world. And so it was basically observing. So we didn't have observational tools. We had to observe with our own eyes. So we could try to map the constellations or whatever we saw in the universe, but it was very hard to gain physical intuition over this. So we could think, for instance, that there were gods that ruled the motion of the celestial sphere, as we know, for instance, from the Greek philosophers. And then only when we started to have the first observational tools, which was with Galileo around the 17th century, so with the invention of the telescope. In this way, we could start making progress in astronomy. So astronomy is basically the activity of looking into the sky and trying to understand the motion of the objects in the sky. Then, since we already had some observational tools, so first the telescope, and then things could get a bit more refined, we had a big breakthrough, which was Newton's gravitational theory, which was basically the first full mathematical description of the force of gravity. So this became the standard description of gravity. And in this period, we could say that we had some observational astronomy, in the sense that we already had observational tools. Then if we think, for instance, about astrophysics, which is something that we also hear quite often, this is more looking at objects, specific objects in the sky, and trying to understand the physics behind such objects. So, for instance, studying how stars form, how the sun forms, how solar systems form. So, looking at particular objects. Then we could only start thinking about cosmology when, in the beginning of the 20th century, we had another breakthrough, which was the replacement of this physical description of gravity by Newton. By Einstein, which published what is called the theory of special and general relativity, which is basically just a reformulation of the gravitational interaction. So this was in the beginning of the 20th century, so it's still very recent, around 100 years. And so we say that cosmology is more of the study of the whole universe. So now we want to understand the evolution of the universe as a whole, as its own system. And this involves not only the observational tools, the laws of physics that come from, for instance, general relativity, all the mathematical tools that we can gather from there. And also we have to think a lot with a critical thinking and philosophical mind, in the sense that we are studying everything basically that exists and how everything interacts in the universe. Okay, so this was in the beginning of the 20th century, and now things started to evolve from there. So then we had another breakthrough, which is called the Hubble-Lemaitre law, which was basically put forward by this gentleman on the right, which is Edwin Hubble. And what he did was he used measurements from the distance to galaxies that were made according to a specific type of stars that are called Cepheids. And we can use these stars basically to gather information about the distance to a galaxy. And then we can map the motion of the galaxy to gain some information about its evolution. Basically, what we see here is this plot on the left that he published. It seems just like a bunch of data points fitted to a line, but what we see here is basically we have on the x-axis, so on the bottom, we see the distance to the galaxies that he observed. And then on the left, on let's say the vertical axis, we see the velocity. So how are these galaxies moving away from us? So basically we observe, we see that they are moving away, we see the distance at which they are, and then we can plot something like this, and we can fit a line. Now, what he found, and may not seem very intuitive, but we'll try to understand what is behind this, is that he found that the galaxies that are closer, they seem to be moving away from us at a slower pace. And instead, the galaxies that are further away from us seem to be moving at a faster pace, moving away from us faster. So this, just by saying this, may not sound very intuitive, but what he concluded was that the universe is expanding. And now we can try to, if we want to understand why this is the case, we can try to make the opposite exercise. So imagine you had everything start in a point and it's expanding. So everything started in a point and it's expanding throughout. Now imagine the opposite motion. So you're on the outside, everything has already expanded, and you're going back inside. Right? We're all collapsing towards a point. So if you imagine everything that is closer to this point, if all has to come together at the same time, whatever is closer has to approach the center slower because it's closer. And whatever is further has to approach the center faster so that it gets there at the same time. So this is basically the thinking that we would have, but the other way around. So everything that is closer has to be moving away slower, and everything that is further has to be moving away faster, such that we can have this expanding motion. So this is kind of the intuitive idea behind this measurement. So what we see here is that we see on the table on the right, what he found was that as we increase the distance, so these are just random numbers just so that we understand the trend. So if once we increase the distance, we will also increase the velocity at which these galaxies are moving away from us. So this was a big breakthrough because it confirmed that the universe is expanding, and we will try to understand what that means. But it was not clear at the time that this had to be the case. So there were other proposals for if the universe was static, didn't evolve, or it could also be slowly collapsing on itself. So it was one of the biggest observational breakthroughs for cosmology, if not the first big one. So then he proposed this that is called the Hubble law, which is what we see here on the purple box, which basically just says this, that the velocity is proportional to the distance. And this proportionality constant is called the Hubble rate, which is this H naught over here in honor of of Edwin Hubble discovering this relation in 1929. Okay, so this established the universe is expanding. So the conclusion from here, also again not straightforward, so this took a lot of research over the years, is that if the universe is expanding, there has to be something powering this expansion, right? So it has to be something that gives it the energy to be able to do so. So then the conclusion was, okay, if everything started in a point and then expanding from there, started in a point, we will understand better also what that means. But this means that the universe could be using the energy that is left from the Big Bang to power this expansion. So it made sense. Okay, so this was the picture at this time. Then now closer to the present, a bit by the end of the 20th century, there was another observation that changed a bit the view on this expansion. So basically, there were two teams that observed that there is observed also the same relation between distance and velocity. But to do this, what they did was they observed a specific type of objects in the sky, which are called supernovae. In particular, a specific type that is called type 1a supernovae. And the reason why these objects are useful is that they are what is called standard candles. So standard candles just means something that has a standard luminosity. So imagine, for instance, the lights of a car, for instance, imagine they have the same luminosity. And so what we can do is, if we have information about the distance, we can also have some information about the velocity, because we know how bright they are. So imagine a car. If you know the car and you know how much it shines, how much the light shines in the dark, you can infer how far away it is by the light. So if it's very close, you'll see the light right in your face. And if it's a bit further, maybe you'll see just a point in the back. And so we can use this, since it's a standard value that we have for the luminosity of these objects. We can use to infer how far they are. Now, what these researchers found is, because now, okay, we have more of these objects, so it's easier to establish a relation, and also we can have objects that are further away. What they found was that actually, not only are they receding from us, so not only are these objects moving away from us faster with larger distances, but also this brightness also decays faster and faster with distance. Now, what they concluded here was that not only was the universe expanding, but this expansion was getting faster and faster by the day. And we say that the expansion is accelerating, but this just means that the more and more time goes by, the faster the expansion is. Now, this is not as intuitive as what we just saw, because even if there is some energy left from the Big Bang that is capable of powering this acceleration, this energy is going to run out, right? So it's going to be spread out as the universe expands. It's not going to keep powering expansion. So if this is accelerating, there has to be something to accelerate it. So for instance, if you have your car you're in the car and there is a road, I don't know, and someone pushed the car, maybe it will keep going because it has some energy that was given to it, and you can use that energy to keep going. But if you're on the highway and you want to accelerate, you need to push for the accelerator for the car to be able to accelerate. So you need to give it gas or electricity or whatever. So you have to power it. And here was the same thing. So if the expansion is accelerating, we have to have something that powers it, right? So we need to have some kind of accelerator that provides this energy. Now, this was already 25 years ago. And since then, there have been many, many other observations that corroborate this observation. So this is now a well-established thing that we try to explain in physics. And in particular, he won the Nobel Prize in Physics in 2011. Okay, so I'll just give you some introduction to some small keywords so that then we can move on with our recipe. So there is another thing that we consider that happened in the universe, which is called inflation. So as the name indicates, inflation is a period where the universe inflated. And it was a brief period right in the beginning of the universe in which there was a very rapid accelerated expansion, and the universe was still really, really young. So it was one of the first instances of its life according to the Big Bang model. And the reason why this epoch must have existed is because we need to explain why, when we look at the sky, the universe looks so homogeneous. Homogeneous in the sense that maybe if I look at that patch of the sky, it will be very similar than if I look the other way to another patch of the sky. Of course, the distribution will not be exactly the same, but I can statistically say that they look very similar, and so they are very homogeneous. And also we measure that they have similar features like temperature. So we need to postulate that everything was very close in the beginning, and then it separated, but because it was close, everything communicated, and there is a reason why everything is so homogeneous. But in fact, this period has another great advantage, which is it also explains the productions of small regions of space in which we have a bit more matter than in others. And because there is a bit more matter there, what will happen is it will try to cluster with other matter around. And these are the regions that will grow to become all the structures that we see in the universe, like galaxies, galaxy clusters, everything. So because we know gravity is attractive, wherever we have a bit more of matter, this will have a bit more of a gravitational interaction, and so it will more easily form the structures. Okay, so this will be one of the ingredients for our recipe. This is what we have to start with. And then we have another component that is called dark matter. So we will speak of two dark components. This is the first one. It's called dark matter. And dark matter is just something that we introduce in the theories and that we observe to exist in an indirect way. And this is very important because it explains some of the most important mechanisms in the evolution of the universe. So first, in order to have this gravitational collapse that I was saying, when we have a small region of space that has more density than the rest, in order for this to be able to keep clustering matter until it forms a bound structure like a galaxy or a galaxy cluster or anything that is bound together, we need a bit more matter that can help this process, and this is dark matter. And then on the top of this, when we observe the motion of galaxies in the sky, we see that actually, if we account for all the luminous matter that we see, that is all the stars or everything that we can directly observe through light, we see that there should be actually much more matter than there is if we are to explain the motion of the objects with our laws of physics. And so for this reason, we have to assume that there is some kind of matter that we cannot observe. So that's why we say it's dark, because it doesn't interact with us in a luminous way, so we cannot observe it through its light. And it's just there to provide this extra gravitational interaction. Okay, now we take a step back and we said, okay, another important thing was the introduction of general relativity by Albert Einstein, which is this fellow on the right. And basically, in very simple terms, what this theory tells us is that there is an intricate connection between geometry and matter in the universe. So basically, this is expressed in the equation that is here. The equation is really not important, but what we want to see is that whatever is on the left gives us the geometry of the universe, and whatever is on the right gives us the matter content of the universe. And because we have an equal sign in the middle, this is telling us that there is some sort of equivalence between the geometry and the matter. So this is expressed here in this drawing on the left, where we see we have some kind of mesh. Let's imagine a towel or whatever. This will be our geometry, our space. And then once we put some matter on this mesh, on this space, what we see is that the matter deforms the space. So imagine, for instance, you have a towel and you put a bowling ball or something very heavy on top of the towel. This will create this deformation. So what this means is, but because I put the matter there, the geometry changed, but also the geometry will tell me how the matter will move around. So imagine now I throw a pebble or something close to that big mass, the pebble will follow the geometry that was induced by the big mass. So this is basically just to say that these two quantities are described in kind of an equivalent way. And so we go back to our original problem, which was, okay, we have this accelerated expansion of the universe, and we don't know how to explain this without introducing something that is powering this motion. Now, if we think of the things we know, whether they could be powering this acceleration, we think, for instance, in matter, and we just said that the matter we know, attracts other matter gravitationally, right? So it's exactly the opposite. We want the unit to power the expansion, but we only have sources that actually tend to come together, to collapse. So we need something else that we're not familiar with and that we have to try to study. So we can either assume that there is something else that we didn't account for in the geometry sector, and this is called theories of modified gravity, in the sense that we change some parameters in the gravitational interaction to try and understand whether the acceleration could be coming from there. Or we introduce another matter component that is very unfamiliar to us because we live in a region, basically in the universe, that is dominated by all the matter around. And this is called dark energy. So this is the one we will consider from now on. Just they are sort of equivalent, but just so that we can have an ingredient for our recipe. So this is another type of matter that we don't know how it interacts, but we know that it powers this acceleration. Okay, so now we have all the ideas that we need to be able to. We did the cuisine 101, and now we can move on to baking our universe. Okay, so let's start by considering that the universe is an olive bread, just so that we can do a parallel with the things we just discussed. So we want to have a recipe to build the universe, to build this expanding universe. And so let's start. Let's see what are the ingredients. Okay, so the ingredients we'll have are exactly the things that I have just mentioned and that we'll see in a bit in more detail. So it's this dark energy, which is something that has a negative pressure, that is to say, pushes against the collapse of matter in order to accelerate its expansion. Then we have the dark matter that I also mentioned, which we need to explain the dynamics of galaxies, taking into account more matter than just a luminous matter. Then we have this big name that is baryons, but this is just the normal matter. So everything we know and everything we study, for instance, in chemistry, so atoms, molecules that make up stars, galaxies, ourselves, anything. And then radiation, which is just light. The light we observe is made of particles of light, which are called photons. And we'll also see in more detail that light gives us a lot of information about the universe. Okay, so before moving to the recipe, let's see then how do we translate this into an olive bread. So then in our shopping list, we will have flour, okay, water, that's how we make bread, baking powder to make it rise, and then some olives to sprinkle evenly. So let's see how this relates with the universe. Okay, so first we have here on the left-hand side, we have this this chart, which basically just tells us how much of the present universe is made of each component. So we will see the components that we just spoke about, and we will see how much goes into the recipe. So how much we observe there is in the universe today. So first we have radiation, which we just saw, it's these particles of light. And radiation basically accounts for 0.1, around 0.1% of the present universe, which is basically very small. And the way we can think of this, it's okay, it's very small, but imagine, for instance, going back to our recipe. If we have our bread, if we turn the oven to different temperatures, we will have a completely different bread in the end. So we'll have different textures. Maybe if it's too high, it will become burned and it will become too crunchy. Maybe if it's too low, it will take forever and then it will be mushy in the end. So the temperature will help us know how the bread cooked. So the whole evolution of the bread since we put it in the oven until the end. So we know that today this is very negligible, but because in the past things were very close together, this was all very energetic. And so because it was very energetic, you can imagine it was very hot. And so there was a lot of radiation bouncing around. When we say radiation, we mean light from the whole spectrum. So not just the light that we can see, but also, let's say, anything like X-rays, infrared, anything that is in the electromagnetic spectrum. And then it also includes another thing, which Professor Benjamin will talk more about, which is the cosmic microwave background, or what we call the cosmic microwave background, which is basically the oldest light that we can see in the universe. So the light that is reaching us now, but was emitted far back in the past of the universe. And so this tells us a lot about the early stages of the universe and also how it evolved until now. Okay, so this is our first ingredient. Sorry?
Sorry.
No.
No.
Okay, so I'll just move on. If you have any questions in the end, maybe I'll be happy to take them. So I was saying we have this radiation that is the oldest light that we can observe in the universe, and that tells us information about the whole evolution. Okay, this is the first ingredient. So let's say the temperature of the oven. It's not really an ingredient, but let's think of it that way. Okay, then we have the other thing that we mentioned, which is baryons, which is this big word for the atoms, molecules, everything we know that forms ourselves in the world around us. So this is, as we see here in the chart, only around 5% of the share of the matter content in the universe today. And so we can think of this as the olives in the bread. So the olives in the bread will be much like the galaxies. If you have the whole of space and you have the galaxies, which are tiny little lumps of matter, this would be the olives. And then you can also think that everything that is around will be kind of the flour that makes up the dough. So this, imagine you're kneading the dough. What you get is maybe some lumps of flour that you will have to try to even out as you go along, but then you will have the galaxies that have form, or the olives spread in the bread. So this is everything that is well understood by physicists in general, and that we have observed for many years, and it's well studied. But we know that it attracts, as I said before, according to gravity, in an attractive manner. So it clusters gravitationally, it tends to come together, which is the opposite of what we wanted for the acceleration. And because this is so well known, it's very straightforward to infer the abundance of this normal matter in the universe, because we can do this with other theories of physics that we can test locally in Earth, and we don't have to look into cosmological scales. Okay, now here comes our dark ingredients. So then we have dark matter, which is the one we already mentioned that we need to explain the formation and dynamics of galaxies. And we can think of this as the wet ingredients that go into the recipe. So like water or olive oil or whatever, in the sense that if I have just flour and olives, I don't have a dough, right? I just have something dry that will come apart at any moment. So if I throw it on the floor, I will just have flour everywhere. But the moment I add a wet ingredient, like water, this wet ingredient binds everything together. And even though we cannot see it directly in the dough or even taste it, because we know water doesn't have any taste, we know that it must be there. Otherwise, things could not be bind like that. So we know that we have to add some wet ingredient. Otherwise, we wouldn't have a dough. We would have just dry ingredients. So this is exactly the same as dark matter does. So it's there. It doesn't emit light. We cannot see it for its light, but we know it must be there in order to bind everything together. So because it's non-luminous, this means that we know that it must either interact really, really weakly with the other sources, otherwise we could observe these interactions, or not interact at all. Then we have our last ingredient, which was the dark energy that we mentioned. Now, remember that dark energy and dark matter, even though they have similar names, they are completely different things. So now this dark energy is around 69% of the total share of the universe's content. And this is now the ingredient that will make things expand, things come apart. So this we can think of as, if we have our olive bread depicted here on the right, we can think that it's like the yeast that we have to put in the bread in order to make the bread rise. And we see that it's not actually the olives that are moving. The olives are just in the dough. It's the dough that it's rising. And when it rises, it brings the olives, carries the olives around with it. So this is the same thing. We have this fluid which has a negative pressure, so it will make the universe expand, much like the bread rising, with the effect of counterbalancing this gravitational attractive character of matter in order to be able to explain the accelerated expansion. So now we have a problem here, right? Which is we have these two components, dark energy and dark matter, on the chart. So the blue and the pink on the chart. And these together account to around 95% of the total universe. So this is a bit embarrassing, let's say, because we have 95% of the total universe that we don't really understand so far its nature, or at least fully understand. But this just shows how we live. We understand what is around us, right? So we start by understanding what's around us, so the ordinary matter, everything that exists around us, and now we are making progress in trying to understand all the other players in the universe's evolution. Okay,
when
so
do
then,
you think dark matter is going to be found? What it is?
so we can do that. Is a good question. So we can observe how dark matter interacts in the universe, but then we can also try to reproduce those interactions in particle colliders, for example, which is what people try to do. So try to observe interactions in which we would expect a dark matter particle to arise. But of course, this, if we think things that happened at cosmological scales, these will be very energetic scales, or things that it's quite hard to reproduce locally in our planet. But again, a lot of progress is being done in this, which is a great endeavor, right? Because we can also observe indirectly through satellites. But good question.
Okay, thank you.
No worries, thank you. And so that's it. We have our ingredients. We can now bake the universe. So we know that we have to start by mixing all the ingredients together. We have the olives sprinkled evenly throughout the dough. So throughout first the flour, then once we add water, so our wet ingredient, this will create the dough. We set it aside. It rises for around 14 billion years, which is the estimated age of our universe. We let it knead for a bit. And then we see exactly that. As the dough rises, the olives, just like the galaxies in the universe, they don't change size, so they remain the same olives, but they will be carried away by the expansion of the dough. So the dough is rising, the olives are rising with the dough, and so they become more spread out. And that is kind of the effect that we discussed that Hubble observed, and then was observed in 1998 for the accelerated expansion. Now, in the beginning, we want to bake it at the maximum temperature, which was what we discussed in the beginning of the universe. Everything is very, very hot and very close together. And this will cause the initial expansion, very rapid accelerated expansion. And then we want to finish off baking with the present temperature of the universe, average temperature, which is around 2.725 Kelvin, which is a unit of temperature that is around minus 270 degrees Celsius. And then I wrote here, tastes better straight out of the oven, in the sense that, of course, we can appreciate that the universe that we have today is the one that is ideal for us to live in. And so we should also, I think, appreciate that everything had to come together over these 14 billion years ago to allow for our existence, basically. Okay, so then just to conclude, today what we have is what we call the standard model of cosmology, which is basically composed out of three ingredients that we have on the left, which are well understood by now, which is the gravitational theory proposed by Einstein, also the way in which we measure distances and we describe the expanding universe as proposed by Hubble, which we see in the middle. And then we have also the normal matter that was like the flour in the dough, which is everything we know, including atoms, molecules, everything that comes from there. Also, I put radiation here because we saw that it's just a small amount. And then we have all these new things that we have just discussed. So we have that early period of acceleration, expanding universe in the early stages of the universe. And then we have the dark matter that we just discussed. This dark matter in the standard model, in this model that we studied, is called CDM, which basically just stands for cold dark matter. So it's cold exactly because we cannot observe it through radiation, through its interaction with radiation, but we know we need it in order to be able to explain the formation of structures. And then we have our dark energy, which in the standard model is this Greek letter, the first Greek letter that is a lambda, kind of like an A without the hyphen in the middle. And this is the component that gives us the accelerated expansion, much like the baking powder in our recipe. And from there, we can build the universe. So our standard model of cosmology. Then as researchers, what we do is if we want to explain some observations that don't go exactly like we were expecting, we can change a bit the recipe in order to have slightly different breads. So it will still be a bread, but maybe it will be a bit more crunchy, a bit more lumpy, maybe a bit more hard, anything. So we can do this by changing proportions of ingredients. Maybe we change the time we let it rise or how much we need it. Maybe we change the type of flour, the baking time, whatever. So this is to say that we can have a recipe that works, but maybe the recipe can still always be a bit tweaked and adapted so that we have the ideal recipe for the universe. So that's it. I hope you enjoyed it. The illustrations are from my friend Inês Viegas Oliveira. You have the website here, which we work together in the publisher. And if you have any questions, I'll be.
I have a question. Can I ask you the question? So first of all, I just wanted to thank you about the recipe illustration. It was very creative and very helpful. I've written down everything, and while I was checking before closing this page, I was thinking. So you mentioned at the beginning that dark matter and dark energy look similar by the name, but are very different. And I really want to know where are the differences and similarities, because here I've written the dark matter is matter, I like the name it has, and it keeps together things, while dark energy keeps expanding. So what is the relation between both of them?
Good question. That is a very good question. They are really different because they're just similar by the name in the sense that we cannot observe them directly. That's why we say they're dark. But dark matter is, imagine, very similar to the atoms and molecules that we study in chemistry, in the sense that it has similar properties, apart from the fact that we know it doesn't interact with light. And because it doesn't interact with light, we cannot see it directly, because everything we see, everything our eyes perceive is light, basically. But in the end, it has the same kind of pressure properties, so it interacts very similarly, and it has possibly a similar mass, or we know that it has to be massive such that it gives mass to the objects, so like galaxies, and it keeps them together. On the other hand, this dark energy is described, imagine, like something that permeates the whole universe. So imagine, for instance, the electromagnetic field. So a bit kind of like this. So you have something that is permeating the whole universe. And this, we can think of this as some kind of energy that is characteristic of the universe. So it is this energy that is characteristic of space, and that it just allows space to keep expanding into itself. So they have very different properties. In the sense, it has to have a pressure that is opposite. So there is a negative pressure that allows for things to come apart.
So thank you very much. Thank you very much, Dr. Teixeira. So